Good evening, Abstract Algebra. It is so great to be with you on a Sunday evening today from my home office. Today we're going to go through a series of problem-solving tidbits, just little bits and pieces that have to do with isomorphisms. Isomorphism is probably the biggest deal concept in abstract algebra because it gives us the only tool that we have to be able to know for certain whether one group is the same as another group, whether the differences that we might see between a group G and a group H are indeed only superficial, and then all of the structure underneath those groups that underlie the algebra and the arithmetic that they define are identical. Two groups that are isomorphic, abstract algebra does not want to see the difference between them. Concrete algebra might, but abstract algebra does not. And so in abstract algebra, our goal, no matter what kind of algebraic structure we study, is we only want to study those structures up to isomorphism. In other words, if two things are isomorphic, we are going to treat them as though they're identical. So this week we saw the definition of what isomorphism is. It's a function from the elements of one group to the elements of the other group that is a bijection, so it is a one-to-one correspondence, one-to-one and onto, and which also not only preserves the elements, but also respects the operations in these groups, such that if I do an operation in one group and then I bring that product over with my function, that the result is the same as if I had brought the elements over first with my function and then did the operation on this side. Right? So operation followed by function is the same as function followed by operation. That's called the homomorphism property. And any function which has the homomorphism property we're going to call a homomorphism. But functions that have the homomorphism property that are also one-to-one and onto, those are the functions that will tell us that two groups are indeed exactly the same as one another under the surface. Those are called the isomorphisms. So what's the agenda for today's problem-solving session? The first thing I want to do on our agenda is to prove a theorem that we sort of talked about when we talked about cyclic groups back in chapter 4, which is to say that every finite cyclic group we can think of in our mind as being just like a group of numbers around a clock with addition as the operation. This is what I like to call the Highlander Theorem. There can be only one. That is to say, any finite cyclic group, if you tell me what its order is, I can tell you a additive group of integers mod n to which it is isomorphic. So every finite cyclic group is isomorphic to z mod n for some appropriate choice of n. And as you might expect, the choice of n coincides with the order of that group. So that'll be the first thing I want to talk about. I'm going to call the clock theorem. And an important corollary to the clock theorem tells us that when n is a prime number, so when you give me a prime number of elements with which to make a group, a corollary of this Highlander theorem, this clock theorem, is going to tell us, therefore, that there is only one way in which I can make a group out of a prime number of elements. Because every group of prime order is cyclic, we knew this in chapter 4, and now we know that every finite cyclic group is isomorphic to a z mod n. Those two things taken together will prove this corollary, that every finite cyclic group of order p, when p is a prime, must be isomorphic to z mod p. So there is only one way in which to make a group with a prime number of elements in it. And that makes the prime order cyclic groups not only cyclic groups which make them the most awesome groups in all of abstract algebra, but they're the awesomest of the awesome, because the prime order cyclic groups are the only way to make any group out of a prime number of elements. That's significant. We get to that today, we're going to have really done something profound. And it's those cyclic groups of prime order that are going to, as we find out in the last act of our course, form the building blocks for all finite abelian groups. Every finite abelian group can be built out of building blocks that are prime order and cyclic, z mod p's, in other words. Then I want to go to an example of how do we use isomorphism in the service of a proof. And so I actually want to go through and prove the order-to-order theorem that says that if you give me an element G in a group capital G, then that element has the same order as its image under any isomorphism from G to another group. So that'll be a chance for us to flex our proof muscles a little bit. We'll do an application that's going to use some of these order and cyclic group properties. One of these came from the homework. Which two of these three groups, U5, U10, U12, are isomorphic? And then also we'll look at U25 as an example. What can we say about the multiplicative group of integers mod 25? And then finally, I want to look through a couple more examples, however many we have time for during our stream today. This one is an interesting one taken out of the homework, which invites us to consider a group which is created from the real numbers by removing the number -1 and defining a binary operation A star B on these real numbers to be equal to the sum of A and B added to the product of A and B. We won't prove that the set G along with this operation forms a group today, but you should verify it on your own. That's a great chapter 2 kind of thing for you to do. But we are going to establish that the group, which is defined on the real numbers without -1 by this binary operation, is actually isomorphic to the multiplicative group of non-zero real numbers. So real numbers without 0 combined with the operation of ordinary multiplication is actually isomorphic to this group. We'll also take a look, if we have time, at a good reason why the additive group of integers and the additive group of rational numbers are not isomorphic as groups. One of the important things that we find out about the integers and the rational numbers when we take an introduction to proofs class, like our Math 180 at Bridgewater, is that these sets, the sets of integers and rational numbers, actually have the same cardinality. There are as many integers as there are rational numbers. Even though one is a proper subset of the other, infinity is funny that way. But this theorem here shows us that there is an actual fundamental algebraic difference beneath the surface in how integers add together versus how rational numbers add together. So we'll provide a justification for why Q and Z are not isomorphic as groups. This is a really good example of a couple of non-abelian groups that we want to demonstrate are not isomorphic. So the dihedral group with a dodecagon, D12. So that's a dihedral group that has order 24. And then there's a symmetric group, S4, permutations of 4 symbols. The order of that group is 4 factorial, also 24. So here are two groups, not abelian, that have order 24. The question is, are they isomorphic one to another? We're going to prove that they're not. So what are some of the ways that we can find a fundamental algebraic difference between these two groups? Not just a difference that's superficial. One of these is a group of permutations, the other is a group of symmetries of a polygon. Superficial differences do not matter for us. We want to find actual beneath the surface differences between these two groups. And then the last one, you probably won't have time for all of these, but here's a group of matrices, 2 by 2 matrices, where the entries in these matrices are taken from Z mod n. So when I multiply these matrices together, their entries are going to combine together using the arithmetic of integers mod n. And we would show, if we get to this problem, that this group of matrices is actually isomorphic to the dihedral group of the n-gon, dn. So this is a lot of different examples. So we're going to kind of start small, start slow. Let's see what we can do, starting at the beginning with the Highlander Theorem, or what I've called the clock theorem. There can be only one. If you give me a cyclic group of order n, then I can give you an isomorphism from that group to the group Z mod n. So let's take a minute or two to think about why this thing should be true. So why does it make sense? Sorry, I'm going to adjust my palette here just a little bit. So why should it make sense for a cyclic group of order n to be isomorphic to Zn? So just going to kind of think out loud here for a minute. What is a cyclic group of order n going to look like? So here we're assuming n is a finite number, right? Well, the very fact that this group is cyclic means, by definition, that a generator for this group exists. So let's call the generator A. And the generator is, first and foremost, an element of my group. But the fact that it's a generator also then means, in turn, right, that all of its powers are capable of generating the group itself. So a to the first power, a to the second power, a to the third power, and so on and so forth. If I run through all the powers of my generator A, I will account for every single element in my group. How many distinct powers of A are there? Well, that's what the order of that element tells me. The order of my generator is the same thing as the order of my group, because it's going to be the same thing as the number of distinct powers that that element has. So by the time I get to the n minus first power of A, if I were to try to go one power further to a to the power n, well, by definition, because my element A has order n, a to the nth power is equal to the identity element in my group. So this a to the n is actually equal to the identity. So what I like to do with that is I like to just loop it back around and write the identity element over here at the beginning. And then I know for sure that this is a complete list of the elements of my group. Right? So here is my group. Here is what every cyclic group of order n must look like. If A is we call A a generator because its powers are going to account for all of the elements, all the n elements of the group G. So then the question that's being asked here is, why is it the case that this group G is isomorphic to the additive group of integers mod n? Well, let's take a moment and list out what are the elements in the additive group of integers mod n. Well, the integers have these familiar names to us, right? The residue classes of integers mod n we typically name by their least non-negative member. So 0 is one example, 1 is an example, 2 is an example, 3 is an example, and so on and so forth. And the largest representative of one of these residue classes that we usually write down is n minus 1, because as soon as we get to n, if you can imagine, n is the same thing as 0 in the additive group of integers mod n, because n is congruent to 0 mod n. So we don't have to write n in my list. And so here are the elements of the familiar additive group of integers mod n. And so the question that we're asking is, why are these two algebraic structures the same? Why is there an isomorphism from one of these to the other? And as you might expect, the way that I've listed the elements here kind of gives away the game. If you look at the similarities between these two lists of elements, what I notice, to my trained mathematical eye, but this is probably, your trained mathematical eye is probably noticing the same thing, is that the exponents that I have up here on my generator and the integers that I have down here in my additive group mod n, those seem to track along with one another, such that if I did this, or maybe let's do it this way. Let's suppose that I draw my arrows facing up, so that if you give me an integer, or residue class of integers mod n, I can produce for you a power of the generator A in my group, right? 1 would, of course, then map to the first power of A. After all, A to the first power is just A itself. And 0 would map to the identity element, which after all is the same thing as A to the power 0, right? So what these green arrows here are doing for me is they're defining for me a function. Let me call it phi. Let me call it 5x equals A to the power x. All I'm doing, right, is I'm taking an integer, or a residue class of integers mod n, and I'm taking and assigning it to the xth power of the generator A. And so then our claim is that this is a one-to-one, that this phi is an isomorphism. Phi is an isomorphism. So let's see if we can figure out how to verify that this function phi is indeed an isomorphism. I'm going to go over into our proof really quickly. I'm going to take this sketch work here that we've done on our napkin, and I'm going to turn that into a first line of my proof here. So in my proof, I'm going to write down, first thing I'm going to write down is the definition for that phi that we just wrote down. Let phi be a function from, and this is a function from Zn to my group, be defined by phi of x equals A to the power x. So I'll compile that, makes it a part of my proof. And of course, the first thing we notice is that I have a surprise symbol in my proof. I have this letter A that the reader is going to have no idea what that letter A means unless I tell them first. So the first thing I ought to do is tell the reader where my A is coming from. Now, where did A come from if we look back at our scratch work? This A came from the fact that G was a cyclic group, and A is therefore a generator. We can choose a generator for that cyclic group. So we'll go in and choose that generator for our readers in the proof. We have to tell them that that's what this A is. Since G is a cyclic group of order n, there exists a generator, A in G, with the property that. And the way I can say this is, first of all, the order of A is equal to n, and second of all, the cyclic subgroup generated by A, in other words, the set of all powers of A, accounts for the entire group. So here's what that line of the proof now looks like. Since G is a cyclic group of order n, there's a generator A with the property that A has order n as an element of this group, and the cyclic subgroup generated by A accounts for all of the elements. Okay, so that now tells the reader where A comes from. It tells me what's the important things I need to know about the element A. And now we've defined our phi. Let's state our burden of proof. We wish to show that phi is an isomorphism. And this would be an isomorphism from Zn to G, right? Notice that there's a subtle difference in what the question is asking here, what the claim in the theorem says. There's an isomorphism from G to Zn. And what we're setting ourselves up to prove here, that there's an isomorphism from Zn to G. So because of that difference, I probably don't want to call this function phi, because I might confuse the reader between the phi that I'm choosing that goes from Zn to G and the phi that's stated in the theorem that goes from G to Zn. So let me call this phi something else. Maybe I'll make it a capital letter phi, just to avoid the confusion. And if I call this a capital letter phi, now I have to explain to the reader why an isomorphism from Zn to G guarantees the existence of an isomorphism from G to Zn. Why does it go both ways? Well, it's going to go both ways because isomorphism is a symmetric relation. And it's a symmetric relation because given any isomorphism from group G to group H, its inverse function is an isomorphism from group H to group G. So all we have to say here is to say that then the inverse phi equals capital Phi inverse will be the desired isomorphism from G to Zn. All right, so now I've stated my burden of proof and I've kind of given away my strategy. I'm not going to construct an isomorphism from G to Zn. I'm going to construct an isomorphism from Zn to G, and then I'm just going to take the inverse of that to give me the isomorphism that we're looking for in the problem. Okay. So now let's go back and remind ourselves of what our burden of proof is going to actually have us do here. If I want to show that phi is an isomorphism, then what I need to do is show really three things. I need to show that phi is 1-to-1. I need to show that phi is onto. And I need to show that phi has the homomorphism property. I need to demonstrate all three of those things in order to show that phi is the desired isomorphism that we're looking for. And again, now remember, we're calling this phi capital Phi, just for the sake of notational consistency with my proof. I need to show those three things. So let's think about how we can show that phi is a 1-to-1 function, for starters. Remember, phi is a 1-to-1 function if whenever phi of G is equal to phi of H, then G must be equal to H, right? It must send different elements from the domain group to different elements in the codomain group, right? I can't send two different inputs to the same output for a 1-to-1 function. Well, this is on our napkin here, so phi of G is going to be A to the power G. Phi of H is going to be A to the power H. And so A to the power G is equal to A to the power H. But then that's going to guarantee, if I multiply by A to the minus H on both sides, that A to the G minus H power is equal to the identity. But if A to the G minus H power is equal to the identity, that means that the order of A must divide G minus H. And if the order of A divides G minus H, the order of A is what we're calling n, remember? N divides G minus H. But if n divides G minus H, that must mean that G minus H is equal to 0, congruent to 0 mod n. And so G must be congruent to H mod n. So there's my napkin scratch work. Let's go back into our proof and write this piece up. So here I want to write the proof of the assertion that phi is 1-to-1. Rather than G and H, let me call my inputs X and Y. Let X and Y be elements of Z n. and assume that phi of x equals phi of y, we will show that x equals y. Right, so there is the strategy and the burden of proof that we're going to use to show that phi is indeed one-to-one. And now all I do is I will recreate that work that I had done on the napkin. So phi of x equals phi of y implies that a to the power x is equal to a to the power y. And that's just by the definition of my function. Right? And then I just multiplied by a to the minus y on both sides to find that a to the x minus y power is equal to the identity element of my group, multiplying by a to the minus y on both sides. So that adds a new line to this part of the proof. And of course, here we go, writing LaTeX code in real time. There's always a couple little errors along the way. So I just multiplied by a to the power minus y. And now is when you use this definition of order, or at least this consequence of order. Most important thing to know is that if I can raise an element to a power and get the identity, that must mean that the order of a, the order of that element, divides that power. This is a theorem about order that we talked about back in chapters 3 and 4 when we were first meeting the concept of order for the first time. And my caution back then, right, was that we cannot conclude from this equation, a to the x minus y equals identity. We can't conclude that the order of a is x minus y, but we can conclude that it's a divisor of x minus y. So we're making use of that fact about order right here. But the order of a is what we called n. And so we've just shown that n divides x minus y. But if n divides x minus y, that means that x minus y is equivalent to 0 mod n. And this is by definition of mod n arithmetic. Right? The very definition of two things being equivalent to one another mod n is that their difference is a multiple of n. Right? And so that's what we're saying here. But if x minus y is congruent to 0 mod n, I can add y to both sides, mod n, to find out that x is congruent to y, mod n. Mod n. And therefore that x equals y as an element of z mod n, as we were trying to prove. So this proves that phi is a one-to-one function. Right? We showed that if phi of x is equal to phi of y, then it must be the case that x is equal to y as elements of z mod n. If we now need to show that this function is onto, let's take the shortcut that we can take anytime we have a function between two sets that have the same number of elements, two finite sets that have the same number of elements. We can't have a one-to-one function between those groups that is not also an onto function. That's an application actually of the pigeonhole principle. So let's just take that shortcut. Since Zn and G both have an equal number of elements, namely n, any function between them, any one-to-one function between them is also onto. And that's just a general result from set theory. So we won't dig too deeply into that result right now. So that will show that phi is onto. Now let's do the final piece to show that phi has the homomorphism property. Let's go back to the whiteboard for a minute. So I want to show that phi has the homomorphism property. And this is the thing that seals the deal for these groups actually being the same, right? So far, we've only shown that they have the same number of elements as one another. We need to show that they're not just the same sets, they're the same groups, and therefore they have the same operation. So what is the homomorphism property going to look like? Well, the homomorphism property is supposed to intertwine the operation of the first group Zn, its operation is addition mod n. It's supposed to intertwine that operation with the operation of the group that we're mapping into, which is G, which has this abstract operation that we're just sort of denoting by a dot here. So what is the homomorphism property going to look like? what is our burden of proof? Our burden of proof is going to be to show that if you give me two elements of Zn, call them x and y, and I apply the operation of my group, x added to y mod n, that the result is going to be phi of x and phi of y multiplied together, multiplication meaning the operation of my abstract group G. So this is the rendition of the homomorphism property for these two groups. So let's just do it. We defined our function by raising a generator a to the power that's identified here. So this left-hand side is a to the power x plus y, where that addition is happening mod n. Meanwhile, on the right-hand side, this is going to be a to the x, where x is treated as an element of z mod n, a to the y, where y is treated like an element of z mod n. So the question is, are these two sides equal? And the answer is yes, they are. But don't be fooled by how simple this actually appears here, that addition mod n, the fact that x and y are elements of z mod n actually means that we really should check that this thing is well defined as well. So if I were to add, let's say I were to add another multiple of n up here on top. So as integers, right? As integers, this would mean that x plus y is to be thought of as x plus y plus some unknown multiple of n. And that x can also be thought of as x plus some unknown multiple of n. Y is to be thought of as y plus some other unknown multiple of n. Right? But here's how I'm going to quickly explain this away so we don't get bogged down in this detail. What's going to happen when I raise a to one of these unknown multiple powers of n? Well, a to the power n is just the identity element in the group G, right? Because a is a generator, therefore it has order n. And so all of these arbitrary multiple powers of n are just going to equal the identity element, and therefore we can neglect them completely because they just cancel out on both sides. And it's easy to persuade ourselves just by the general properties of exponents that that equation, a to the x plus y is equal to a to the x times a to the y, proves our homomorphism property for us. So let's write up that bit so we can be done with this theorem, and then we can quickly go to a couple of the corollaries before we move forward. So here we'll prove that phi is a homomorphism. We will show that for all x and y in z mod n, we have phi of x plus y is equal to phi of x times phi of y. Right, so again, we're cluing the reader in to the strategy of the proof and our burden of proof. We're going to show for all x and y in z mod n that this equation here is satisfied. And so we'll just repeat those steps. Phi of x plus y. Ooh, surprise symbols. Sorry. I have a for all assertion here, so I need to say let x and y be elements of z mod n arbitrarily chosen. Right. And then I'm going to take phi of x plus y, and that addition again is happening mod n. And I'm going to say that what this is equal to is it's equal to a raised to the power of x plus y plus some unknown multiple of n, or some k in the integers. And this is by the definition of our function. It's also by the definition of mod n arithmetic. So there's my first line. Okay. I know that this is going to be a to the power of x plus y plus some unknown multiple of n. But then we can use the properties of exponents to say that this is equal to a to the x times a to the y times a to the power kn. Properties of exponents. So no magic deep thoughts going on there. We're just using properties of exponents. And now we can use the fact that a to the x, a to the y times identity, since a to the power n is equal to the identity. We know a to the power n is equal to the identity because n is the order of the element a. So all I've done here is I've done that promised cancellation, right? A to the power kn. But then a to the x, a to the y times identity is just equal to a to the x times a to the y, which in turn is equal to phi of x times phi of y. And this is just by definition of the function phi. And that gets me to the end of the thing that I'm trying to prove. As soon as I fix my typo, I've got this piece back. And so now, thus, phi is a homomorphism. And we have verified all three properties that make phi an isomorphism, as desired. So this seems like a lot of talking, a lot of writing, a lot of what Mr. T would call jibber-jabber, right? Some of this is what algebraists call abstract nonsense. I mean, it seems like we're just kind of pushing some symbols around. But we're really getting a profound result, right? This is the Highlander Theorem. There can be only one. If you give me a cyclic group, a finite cyclic group, and you tell me what its order is, here's a cyclic group of order 144. I can tell you that whatever your group might look like on the surface, under the surface, it is exactly the same thing as the additive group of integers, mod 144. Right? There's an isomorphism, and this is the isomorphism. This is what I was talking about when I said, back at the beginning of talking about cyclic groups, that a mental model for all cyclic groups should be that all finite cyclic groups look like a clock. And they all look like a clock because they're all isomorphic to one of these standard additive mod n clock addition modular arithmetic groups. So there's only one structure we can make that's a cyclic group of finite order n. So let's move forward off of that into a corollary, because this is where things really start to get juicy. What we're ultimately trying to do in this last part of our abstract algebra course is to figure out how many different ways are there for us to build a group from a set of elements. And this next corollary gives us a really profound piece of that answer. The corollary reads as follows. It says that if you give me a prime number of elements with which to make a group, there is only one way in which I can turn those elements into a group, and that is to turn them into a cyclic group of prime order. And therefore, according to our theorem, I'm going to build a group that's isomorphic to Z mod P. So what we can kind of say that this corollary means is that Z mod P up to isomorphism is the only group of order P. So I'm just going to kind of put that observation into quotes here, because that's really what the import of this statement is. The additive group mod P is the only group with P elements. And that is a big statement, right? That is something I can't understate the importance of statements like that. Right? It's what we call a classification theorem. It tells me what the algebraic structure of a group must be only by knowing how many elements it has. That's a really rare thing. And the primes are really one of the only places where we can reliably make such a sweeping claim. So let's just write the proof for that. I've already talked our way through it. Let's just put the words down onto the page. And it relies on these two facts. The first one is one that we established back in chapter 4 when we were first talking about cyclic groups. Back in chapter 4, we had the theorem. I forget what the name of the theorem was, so we'll just call it the prime order theorem. By the prime order theorem, every group of prime order is a cyclic group. And thus, G must be cyclic, right? Because the hypothesis here is that G has a prime number of elements, right? And by the prime order theorem, therefore we know that G is a cyclic group. But, hence, by the Highlander theorem, the clock theorem, the thing that we just proved, G is isomorphic to the group ZP. And that's all there is to it. I mean, the nice thing about mathematics is that once you prove something, no matter how much work it takes to prove it, once you prove it, it's proven, and then you can use it. And this corollary is a really sweeping statement. But by the time we put in all the effort to prove the prime order theorem back in chapter 4, and to prove the Highlander clock theorem that we just proved in this chapter, now the proof of this really sweeping statement is only 2 lines long. If you give me a finite group of order P, I know it must be cyclic by chapter 4, and now I know that therefore it must be isomorphic to an additive group mod P, according to what we just proved. So Z mod P is the only group we can make up to isomorphism that has P elements in it when P is a prime number. So Z mod 2, Z mod 3, Z mod 7, Z mod 101, those are the only groups of their order up to isomorphism. We can't do anything else with a prime number of elements. I think that's really cool. I'm going to pause here for just half a minute. If you're watching us live and you're one of my students this semester, feel free to be interacting with this conversation over Slack in our Slack channel. I'm monitoring that. If you're watching on Twitch today and you're not a part of our class, drop questions into the Twitch chat as well. I'll get them either way, and I can certainly help to respond to them while we're in the process of solving more stuff today. So let's start moving ahead in our agenda. So what's the next bit that I want to get to? So we did the prime order implies unique part. Now I want to look at a couple of applications. One of these came from a homework problem, and the other one is just one that I selected that's going to give us another opportunity to think about the multiplicative groups, the UNs, multiplicative groups of integers mod n. So I'm going to kind of talk about both of these things simultaneously, both of these problems simultaneously. One of the big questions that we're going to be able to answer in Chapter 8, which weirdly enough is going to be the next chapter that we do. We're going to skip 7 and then come back to it. But in Chapter 8, where we talk about direct products of groups, we find out what the structure of the U groups actually is. Find out what the deal is with the UNs. What can we say about the UNs just by knowing what the value of n is, right? So we're going to find a more general answer to these two problems once we get to Chapter 8. For right now, I've got 4 different U groups that I want to try and understand in this set of 2 problems. So let's take a quick moment and just run down the line and figure out as much as we can figure out about these groups. So U5, U10, U12, and U25. First of all, remember that because we're using the letter U here, that notation indicates that these are groups with the operation of multiplication with the appropriate modulus. So U5 is the integer residue classes mod 5 with the operation of multiplication mod 5. Right? So don't lose sight of the fact that that's the operation that we're working with here. And I won't write that for the others. Let's take a moment, first of all, and figure out what the order of each of these groups is, because that's going to give us a chance to reacquaint ourselves with the Euler-totient function, the Euler phi function. Because after all, in order to be a residue class, an multiplicatively invertible residue class mod n, a number needs to be relatively prime to n. And so the number of multiplicative units, multiplicatively invertible elements, mod n, is going to be phi of n, which exactly counts the number of relatively prime natural numbers to n that are less than n. And so the order of U5 is going to be phi of 5. Well, 5 is a prime number, and so we could use our shortcut, but I kind of like using the full formula if we can. 5 to the 1 minus 1 times 5 minus 1, right? Where this 1 here is coming from the power that exists on my prime, right here in my 5. So 5 to the first power. Phi of 5 to the first power is 5 to the 1 minus 1 times 5 minus 1. That's going to be 1 times 4. So there's 4 elements in U5. If we go down to phi of 25, let's do this last one real quick. Phi of 25, since 25 is 5 to the power 2, we can use that same formula for the Euler phi function that computes the phi function of any prime power and get that this is going to be 5. Let me hide my write-up window here for a second. 5 to the power 2 minus 1 times 5 minus 1. 5 to the power 2 minus 1 is going to be 5, of course. 5 minus 1 is going to be 4. And so 5 times 4 is going to give me 20. Ooh. So there's a lot of elements in U25. A lot more, certainly, than U5, U10, and U12. Let's quantify the others. The group U10 is going to have phi of 10 number of elements. Well, 10 is not a prime power. So remember, if we want to find the Euler-totient function of 10, we first need to find its prime power factorization. 10 is 2 times 5 as a product of prime powers. And since 2 and 5, like any pair of powers of distinct primes, are relatively prime to one another, And because the Euler phi function is multiplicative, that is what lets us split apart phi of 2 times 5 into phi of 2 times phi of 5. Now we can use the prime power formulas for each of those two. Phi of 2 is 2 to the 1 minus 1 times 2 minus 1. Phi of 5 is 5 to the 1 minus 1 times 5 minus 1. Well, a lot of this stuff goes away. That's 1, that's 1, that's 1. 5 minus 1 is 4. And when I do the same thing for U12, well, 12 is going to be 4 times 3. So let's call it 5, 3, and 5, 4. Right? Those are my prime powers that multiply together to give me 12 in the prime factorization. 4 is 2 to the power 2. And so when I use this formula, I'm going to get 3 to the 1 minus 1 times 3 minus 1 times 2 to the 2 minus 1 times 2 minus 1. And again, just want to color code these so that we know where these parameters are coming from. Right, 3 to the power 1 accounts for that 1 right there. And now when I do all of this arithmetic, this is going to give me 1 times 2 times 2 times 1. So actually this turns out to be 4 as well. So the first thing that we notice just from these Euler phi calculations is that out of this set of 4 multiplicative groups, 3 of them have the same order as one another. These first 3 groups here are groups of order 4. The group at the end here is a group of order 20. So one thing that we know for sure, sorry, I got to plug my Apple Pencil in here really quickly. One thing that we know for sure is going to be true is that this 4th group cannot be isomorphic to any of the other 3. Because isomorphisms preserve the order of groups. And so a group of order 20 cannot be isomorphic to a group of order 4. It's not a possibility. What is a possibility, and this is the point of our question that we're about to tackle, is that some of these different groups of order 4 might be isomorphic one to another. But they're not necessarily isomorphic just because they have the same order. Remember, all of these isomorphism properties are sort of one-way implications. If G is isomorphic to H, then the order of the group G agrees with the order of the group H. But it is not the case, in general, that the converse holds. Converse is not true in general. Right? It may be true in some cases, but it's not, we can't guarantee that just because the order of 2 groups is the same, they're not necessarily isomorphic. So let's try and be thoughtful about how we understand these groups. We're going to set U25 off to the side for a minute. It's got 20 elements. I don't want to write them all right now. But we can, if we want to, explicitly write out the elements of each of these groups of order 4. U5, its elements are 1, 2, 3, and 4. Mod 5. U10, all of the numbers less than 10 that are relatively prime to 10. That's going to be 1, 3, 7, and 9. Mod 10. And then meanwhile, U12, all of the natural numbers less than 12 that are relatively prime to 12. That's going to be 1, 5, 7, and 11. Now, to figure out whether these groups are indeed, which of these groups are isomorphic to one another, because I'm guaranteed here by the statement of the problem that exactly 2 of them out of these 3 are indeed isomorphic. Let's try and be savvy. Let's try and use something that we just learned and ask ourselves the question, are any of these groups cyclic? Can I find a generator for them? Because if yes, then the group that is cyclic is going to be isomorphic to Z mod n. And so if I find, and where n here is equal to the order of the group, right? Z mod 4. So if I can find one of these groups that's cyclic, it's going to be isomorphic to Z mod 4. If I can find 2 of these groups that are cyclic, then they're both isomorphic to Z mod 4, and by the transitive property of isomorphism are therefore isomorphic to one another, with Z4 forming the bridge between the 2. This is like the example that we just did this past week in class with U7 and U9. We showed that they were both isomorphic to Z mod 6, the additive group, and therefore we can make a composition of 2 isomorphisms that shows that they're isomorphic to one another, using the transitive property of isomorphism. So let's see if we can figure out whether any of these are cyclic. To figure out whether they're cyclic, let's ask ourselves, again, just to get practice, how many generators, how many choices of generator would there be? Well, that answer is also answered by the Euler phi function, right? There's going to be phi of 4 possible choices of generator. What is phi of 4? Well, 4 is 2 squared, so phi of 4 is 2 to the 2 minus 1 times 2 minus 1, and that's 2. So what this is telling me is that if any of these groups are cyclic, then in that group there will be 2 different elements, each of which has the power, pun intended, to generate all the elements of that group. There's 2 different generators, 2 different choices of generator for a cyclic group of order 4. And we know that 1, which is the identity element, is not going to be a generator for any of these groups. So the first thing that I want to try in my problem-solving process here is I want to pick the next largest number, maybe 2, 3, 5, and figure out whether each of those numbers can indeed generate the whole group that it participates in. Let's try it with 2 in Z mod 5. Not Z5, sorry, U5. In U5, we want to look at what are the powers of 2. Do they generate the whole group, or do they fall short? Well, 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4, mod 5. 2 to the power 3 is 8 as an integer, which mod 5 is equal to 3. And that indeed accounts for all of U5. So, what that calculation shows me is that U5 is cyclic because 2 is a generator. And so, the moral of that story is that U5 is isomorphic to Z4. According to the Highlander Theorem, right? Showing that it's cyclic and has order 4 implies by that theorem that it's isomorphic to the additive group of integers modulo 4 in this case, the order of that group. So U5 is isomorphic to Z4. Let's check 3 as an element of U10 and see what happens. Does 3 have the power to generate all the elements of U10? 3 to the 0, 3 to the first, 3 to the second, 3 to the third. Let's see what happens. 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, which is mod 10, it's still equal to 9. I multiply 9 times 3, 9 times 3 is 27, mod 10, which is 7. And sure enough, we find out that U10 is also a cyclic group of order 4. And therefore, by our Highlander theorem, we know that U10 is isomorphic to Z4. But, just like our example from class, once I know that U5 is isomorphic to Z4 and U10 is isomorphic to Z4, all we have to do is tiptoe through the tulips, right? To get an isomorphism from U5 to U10, I'll just go from U5 to Z4 via an isomorphism, and then from Z4 back to U10 via its isomorphism. Right? So U5 is isomorphic to U10. And we don't have to come up. One of the other beauties of the Highlander theorem is that we established this isomorphism without having to concretely come up with a formula for the isomorphism between these U groups. I know that in our class examples, we did a lot of examples where we were concretely writing down a formula to establish 2 things are isomorphic. But if you have a theorem like this, and you can cite a theorem like this, draw from the authority of a theorem that we've proven, that's how mathematics works. And so if we can draw from that theorem, we don't need a formula for this isomorphism. The theorem says there exists an isomorphism from U5 to Z4 because we showed that U5 is cyclic. And that there exists an isomorphism from U10 to Z4 because we showed that U10 was cyclic. And therefore, again, by the transitive property of isomorphism, there is an isomorphism from U5 to U10. It's gotten by composing this isomorphism with the inverse of that one. So U5 is isomorphic to U10 for that reason. So what about U12? What can we say about U12? Well, let's kind of do the same thing that we were doing a minute ago and figure out whether 5, for example, can generate all the elements in U12. So in U12, 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3. What do we get? 5 to the 0 is 1, 5 to the 1 is 5. 5 squared as an integer is 25, but mod 12, that's equal to 1. Multiply that by 5 again, I only get 5. And so I am not getting all the elements of U12. So 5 is not a generator for U12. Which means that we should probably check to see whether 7 is a generator. So just move up to the next one. 7 to the first power is 7. 7 squared is 49, but mod 12, that's equal to 1. So 7 is not a generator either. And 11 has the same problem. In fact, once we rule out 5 and 7, we can actually stop. Because we know, again, by the Euler-Toshin function, if our group was cyclic, since it has order 4, there have to be 2 choices of generator. But we know 1's never going to work because it's the identity. It doesn't generate any non-trivial group. And 5 and 7 don't work. And so 11 cannot work because there have to be 2 generators, 2 choices of generator for this group. And there can't be more than 1 if 11 does indeed work. And so therefore 11 cannot work. Or we could just have done the arithmetic. So we find out that U12 is not cyclic. And since U12 is not cyclic, that means that it cannot be isomorphic to the other 2 examples that we have here. So we established, again, U5 and U10 were isomorphic. They were isomorphic because they were both in turn, as cyclic groups of order 4, they were both isomorphic to Z4. And therefore, by the transitive property, isomorphic to one another. Meanwhile, U12 is out here on its own, and it's not isomorphic to either of the other 2. One of the reasons that a cyclic group cannot be isomorphic to a non-cyclic group is because of the theorem that we're about to talk about next. And that's the theorem that says that isomorphisms preserve the order of elements. If you give me an element of a given order in G, then if I map that element into another group H by an isomorphism, that H will have the same order as G did. This is going to be a relatively straightforward, relatively quick proof. And because I want to make sure we have time to get to some more examples, let's try and work our way through this proof before we go forward. So how do we know that isomorphisms are going to preserve order? That if phi is an isomorphism from G to H, then the order of any element G is equal to the order of phi of G. Well, let's get ourselves a little bit of scribble space here. So over on my cocktail napkin, I'm going to imagine that I've got an element G in my group G over here. Whoops, I'm writing off the top of my screen here. So I've got, still moving stuff around, sorry. So I've got an element G in my group big G. And then my isomorphism, which we're calling phi, right? It's an isomorphism, so with a little isomorphism symbol under here, is mapping, it's sending my element G over to an element phi of G. Just for the sake of simplicity, I'm going to give that phi of G a name that's a little easier to work with. I'm going to just call it little h. Okay? So the element G in this group is getting mapped to the element H in the other group. Maybe I'll draw a little mini hunters and arrows diagram just to be even more visual with this. So there's the group G, there's the group H. I've got an element G in the former, and I've got an element little h in the latter. And those two are related by my isomorphism. So G maps to H by my isomorphism phi. Also, each of these groups has an identity element. Let's just write those in. Let's call this one EG, and let's call the other one EH. Just so we can keep straight which identity element goes where. They are groups after all, so they have to have identity elements. And now I realize that my own head, my big melon, is getting in the way of this diagram. So my apologies. This is my first week trying out this this green screen, which is super cool, but I feel like a TV weatherman who is trying not to get in the way of his weather maps along the way. Okay, so we need to figure out why the order of G agrees with the order of H. Why should that be true? So first of all, let's just do the proof for the case in which G has finite order. So let's suppose that the order of G is equal to n. Okay. The infinite order case is not really any more complicated. I invite you to write up those details on your own if you like. So what does it mean that the order of g is equal to n? This means in particular that the nth power of g is equal to the identity. It also means that n is the smallest such power for which that holds true, right? But really the thing we most are going to care about in this proof is that the nth power of g does indeed equal the identity. What does the nth power of g really mean? It really means the result of taking g and just combining it with itself with the operation of my group a total of n times, right? An n-fold operation. And this is the identity element of the group G, of course. And so here is the magic sauce. Here's the reason why I wanted to talk about this proof with you today, is that when you use a homomorphism in a proof, notice I said homomorphism, not even isomorphism. When you use a homomorphism in a proof, most often what you're using it to do is to take an equation that involves elements in one of my groups and transform that equation into an equation that tells me something about elements of another group. Right? So I have here an equation that has only elements of G in it. I want an equation that can tell me something about elements of H instead. So I'll just apply my function, which is a homomorphism, that'll turn all my elements from G into corresponding elements of H. And this is why it's magic. If I take phi and I apply it to both sides of this equation, then starting on the right-hand side, I've got phi applied to the identity element of G. Well, what do, in fact, not just isomorphisms, but indeed all homomorphisms do with the identity element of a group? They map it to the identity element of the other group. That is something that every function with the homomorphism property will do. Just like how in linear algebra, every linear transformation mapped the zero vector of the domain to the zero vector of the range. Because the zero vector is nothing more than the identity element of the additive group that underlies the vector space structure. And a linear transformation, among other things, is a homomorphism of those additive groups. So for the same reason that linear transformations send zero vector to zero vector, every homomorphism sends identity element to identity element. And so this right-hand side of my equation, phi of E, is just going to be E, where that E is the identity element of group H. So when we sort of cross through the looking glass here, that's what homomorphisms are kind of doing for us, right? They're taking us from the land of everything is G to the land of everything is H. Right? We're crossing over the Rubicon here. Now everything's going to be an element of H, and the identity goes to the identity. Well, what's going to happen with this n-fold product of G's? G times G times G times G done n times. Well, now again, we can use the homomorphism property to tell me what's going to happen over here. Right? Because this phi has the homomorphism property, that tells me that phi of G times G is going to be phi of G times phi of G. Instead of doing all the multiplications of G with itself to give me the identity over in my group G on the left, so think of this as multiplying G by itself n times is going to give me the identity element. Right? Instead of doing that operation in G, because phi is a homomorphism, I can choose to do it over in H instead with the images. So phi of the nth power of G is nothing more than the nth power of phi of G. So this is just going to be phi of G multiplied by itself n times. That's the magic of homomorphisms, right? And each of those phi of G's is H. So I'm going to have here H to the power n is equal to the identity element of the group H. All right, there was the important step, right? Now that I know that the nth power of H is equal to the identity in H, what do I deduce about the order of the element little h? Again, carefully think about it. The nth power is equal to the identity. That doesn't mean that the order of H is equal to n, but it does mean that the order of H divides n. Right? So this piece of the argument shows that the order of H divides n. But that wasn't supposed to be enough for us, right? We need to show that it's not just a divisor of n. We need to show that it's equal. So how are we going to do that? the one thing we haven't done yet in this proof is we haven't fully used the fact that phi is an isomorphism. We've used the homomorphism property up until this point, but we have not used the one-to-one and onto component of this function. Right? We haven't fully realized the fact that phi is an isomorphism. And so to do that, here's the sleight of hand. Every isomorphism has an inverse function which is also an isomorphism. And so everything that my phi can do, my phi inverse can do backwards, right? Going from h to g instead. So all I have to do is run this same argument, but run it backwards. Run it with h's in place of g's. And that will actually give me exactly what I'm looking for. So I'm just going to kind of be really crude here and just sort of write every g that I have here, I'm going to replace it with an h. Right? So if the order of h were equal to n, then the nth, well, I guess we're starting from here. The nth power of h is equal to the identity element of h. But then I'm going to use not phi, but phi inverse of h times h times h times h, done n times, right? And then use the homomorphism property that the inverse of phi has, because the inverse of a homomorphism is, an inverse of an isomorphism is an isomorphism, and therefore has the homomorphism property. And then since the inverse is an isomorphism, it sends the identity to the identity. And so phi inverse of EH is going to be EG. Phi inverse of each of these h's, phi inverse of h times phi inverse of h times phi inverse of h, etc., etc. Each of those phi inverse of h's, because h is a one-to-one function, if phi of g is equal to h, that means phi inverse of h is exactly equal to g. So each of these is equal to g. There's a total of n of them. And so I have on the left-hand side here, g to the power n is equal to the identity element of g. And if g to the power n is equal to the identity element of g, that must mean that, and now I've screwed this up, that must mean that the order of g divides n. All right, so that's not quite, how did I want it here? I think I wanted not to use the letter n here for this. What I wanted to do is I wanted to say, let's suppose that the order of h. All right, so let me just write in English the argument that I was trying to make. The first step that we did is we said, if the order of g is n, then the order of h divides n. That was the first thing that we said. And then the second thing is, let's suppose that we let m equal the order of h. So I probably should have made this an m, and then we run through this whole argument here. So let me turn all those n's into m's. My apologies for messing this up on the fly here. M. And we did that m times, so we end up with an m here. And so order of g divides m. If m equals the order of h, then the order of g divides m. And so all in all, what did we end up proving here? We ended up proving that the order of g divides the order of h, and that the order of h divides the order of g. So the orders of g and h are each divisors of one another. And in number theory, that can only mean one thing. It can only mean that they're equal. And so that ends up being the napkin version of this proof. Let's just write it up really quickly. Take a gander at what's on this screen. It's a little bit messy. I'm going to try and rectify the issues with that presently as we try and write up this argument. So why do isomorphisms preserve order? Let's just get this bit written up, and I'll try to make it a little more straightforward than what we just had. So what I'm going to do is just right off the bat, I'm going to let readers in on the notation that I ended up settling in on here. I let n stand in for the order of g, and m stand in for the order of h. So let's define that right out of the chute. And again, this is just the proof for the finite order case. So let n equal the order of g, and let m equal the order of phi of g. Since we were using h in our proofs, let's also make that a part of my notation I define here at the beginning. Let h equal phi of g. n equal the order of G, and m equal the order of H. So we're just defining some time-saving notation at the outset of this proof. And so let's clue the reader in on the ultimate strategy. Remember, the ultimate strategy, the way that I ended up finishing my argument, is we're going to show that each of those numbers is a divisor of the other, that n divides m, and that m in turn divides n. So we will show that both n divides m and m divides n. This will guarantee that n is equal to m. So the only way to have two numbers, each of which is a divisor of the other, is for those numbers to be equal. All right, so how does this work? So we'll run the argument first going forward, using the order of G. Since n is equal to the order of G, we have, and then here comes the magic calculations that we did in our napkin version. Since n equals the order of G, we have G to the power n is equal to the identity element of G. That's by definition of order. Then I just apply my phi to both sides. Right? So far, all we've done is we've just used the definition of the order of an element. G to the n is equal to the identity element, and then I've just applied phi to both sides. Now comes the magic. Right? We use two properties that every homomorphism has. We use the fact that the product rule, the homomorphism property, implies that phi of the nth power of G is the nth power of phi of G, and also that phi of the identity element of G gives me the identity element of H. By properties of homomorphisms, not just isomorphisms, but all homomorphisms have these two properties. So that is where the magic happened. It's this third, going from the second line to the third line right here. That's really where the cool stuff, where the important heart of the proof happens. Because now all I have to do is replace phi of G by H. And I get the observation that H to the n is equal to the identity element of the group H. And therefore, that the order of H, which is equal to m, is a divisor of n. And that's by properties of order. Probably the most useful fact about order, right, is that if any power of an element gives me the identity, then the order of the element divides that power. So this proves that m divides n. Now, since phi is an isomorphism, there exists an inverse function, phi inverse, from h to g, and, moreover, g is equal to phi inverse of h. Right? Coming back to the diagram for just a second, right? The fact that phi has an inverse function means that if phi sends g to h, then phi inverse necessarily sends h back to g. There is no possible room for disagreement or ambiguity there. So g is equal to phi inverse of h. Now we just have to run this same argument about the order, just using the order of h instead of the order of g. And that will complete our proof that n divides m. Since m is equal to the order of h, we have, and now it's the very same argument from before, h to the m is equal to the identity element of the group H. Now I'm applying the inverse function, phi inverse, to both sides. Phi inverse of h to the m is equal to phi inverse of the identity element of H. And again, no real information content there other than that phi inverse is a function, so I can apply it to both sides of an equation. Okay, but now is when the homomorphism property helps us again, right? Because phi inverse is a homomorphism, phi inverse of h to the power m is the mth power of phi of h. And phi inverse of the identity element of h is the identity element of g. Since phi inverse is a homomorphism. Right? That's, again, this third line is the magic line here. Since phi inverse is a homomorphism, we can apply the product rule and we can send identity to identity. And then phi inverse of h is exactly g. G to the mth power is equal to the identity element of g. And therefore, the order of g, which is n, divides m. And that's, again, by properties of order. So let me give you the sort of Star Wars opening crawl here on this one. So if h is phi of g, n is the order of g, m is the order of h, then we showed that m must divide n, because the nth power of g is the identity, guarantees the nth power of h is the identity, and therefore that the order of h divides n. And then using the inverse function, which is also a homomorphism, and actually an isomorphism, the mth power of h is the identity, guarantees the mth power of g is the identity, and therefore the order of g, which is n, divides m. Thus, since both n divides m and m divides n, we have n equals m as desired. And that gives us a proof that homomorphisms preserve the order of elements. If you give me an element of a given order in a group G, its image under an isomorphism will have exactly the same order as the element G had. One thing I want to mention about this proof before we go forward. So we only needed to use the fact that phi was an isomorphism. We only needed to use it for the second half of our proof. We only needed the fact that phi was an isomorphism here to show that the order of G divided the order of H. We could do the whole first part of this proof only by knowing that phi was a homomorphism. So when we talk about homomorphisms in more generality in chapter 10, we actually end up using this as one of our properties that all homomorphisms have, that the image of any element under a homomorphism has an order that divides the order of the original element. So if you give me an element of order 12 and I map it with a homomorphism, then the image will have to have either order 12, 6, 4, 3, 2, or 1. It could have any one of those, but the order here has to be a divisor of the order here, when we just have the homomorphism property and not fully an isomorphism. But when we have an isomorphism, that goes both ways, and that's what makes the order have to exactly be the same in both cases. So let me pause here for about 20 or 30 seconds. If you're watching live, I still want to do a couple more examples, so we're going to go a little bit long on today's live stream, but that's okay. I want to look at some of these other is it isomorphic, is it not isomorphic examples before we wrap up. But if you have questions that you want to make sure get addressed and you're watching live this evening, contribute those in the next 20 or 30 seconds. I'm going to get things ready for our next set of exercises. All right, so I want to get to a couple of examples of demonstrating whether two groups are or are not isomorphic, paying particular attention to the are not question. So we're going to spend these last couple of problems developing some tools for distinguishing, for highlighting differences in the algebraic structure of groups. And so both of these problems we're about to look at right now have the form prove that such and such is not isomorphic to such and such. So we're going to start with this example, which uses a symmetric group of permutations of 4 symbols, S4, and a dihedral group, the group of symmetries of a regular 12-gon. And we want to show that these two groups are not, in fact, isomorphic to one another. So we need to find a difference. We need to find something that they don't agree upon. And keep in mind that the tools that we've developed, particularly in today's live stream, to distinguish between groups, one of them is the cyclicity test. Right? That two groups that are cyclic and have the same order are going to be isomorphic. Therefore, if I have two groups, one of which is not cyclic and the other of which is, then we know that those are not going to be isomorphic to one another. Also, even if they are cyclic, if they have the same order, or if they have different orders, rather, of course, they're going to be not isomorphic to one another. We also developed this order-to-order theorem. And this is probably the most powerful and the most commonly used tactic, particularly in introductory group theory, to find differences between two groups. The most convincing way is to show me an example of an element order that one group has that the other group doesn't. So G has an element of order 17, but H does not have an element of order 17. Therefore, they cannot be isomorphic, because if they were, the image of this order 17 element would be an order 17 element. And if there doesn't exist one on this side, that would arrive at a contradiction. So that's the general shape of how most of our differences that we find between groups get surfaced in this part of group theory and abstract algebra. So let's tackle this problem. How do we prove that the dihedral group of the dodecagon is not in fact isomorphic to the symmetric group S4? This is going to be a problem that requires us to really understand these two groups really as intimately as we can. So let's start with that. and figure out what it is that we can say about D12 and about S4. So first of all, the first test that we usually do for finite groups is just to test how many elements they have. D12 is the dihedral group of the dodecagon. And like any dihedral group, its order is equal to twice the number of sides on my polygon. So the order of the dihedral group Dn is 2n, but here n is equal to 12. And so the order of D12 is 24. So there's 24 elements. Probably not going to write them all down, but at some point we're probably going to write down a number of them. Meanwhile, S4, the symmetric group on 4 symbols, the group of permutations of 4 symbols, that order is 4 factorial. But 4 factorial is 4 times 3, which is 12, times 2, which is 24. And so the first thing that we notice is that these are two groups that have the same order. And so they might be isomorphic. Right? This is an example of a necessary condition for isomorphism, but not a sufficient condition for isomorphism. It just means that we need to keep looking. We have not yet found a reason that these two groups should disagree. So let's look closer. And let's try and use that order-to-order theorem that we just got done proving, that says that isomorphisms preserve the order of elements in our two groups. And so if I can find an example of an element of a certain order that one of these groups has that the other group does not, then we will be exactly where we need to be. So let's get up close and personal with D12 and with S4 for a minute. Let's start with S4. What are the elements of S4 going to look like? Well, these are all going to be permutations on 4 symbols. And we know that every permutation can be expressed as a product of disjoint cycles. So we can classify the algebraic behavior, in particular the order of these elements, by the types of cycles, by the lengths of the cycles that compose together to make them up. So there's going to be one cycle type that is just the identity. So call it 1 plus 1 plus 1 plus 1. There's going to be one cycle type that is just a single transposition, 2 plus 1 plus 1. There's going to be another cycle type that is a product of 2 disjoint transpositions. So a 2 cycle composed with another 2 cycle. There's going to be another cycle type that is a 3 cycle composed with a 1 cycle, so it's just a 3 cycle, which is the so it's just a 3 cycle. And there's going to be one more cycle type, which is a 4 cycle. So this is just sort of a pictorial representation of what all the 24 elements of S4 are going to look like. And the beautiful thing about the symmetric group is that the cycle type completely determines the order of a permutation, using the least common multiple of the orders of the cycles, because disjoint permutations commute one with another. So we can do the following. We can say what the orders of each of these cycle types end up being. Let's list them all out. This is not going to be a practical way to do things in every case, but we only have 5 cycle types to work with. So this seems like a reasonable thing to do. So the identity permutation, of course, is going to have order 1. The 2 cycle, a single transposition, that's going to have order 2. A product of 2 disjoint transpositions, its order is going to be the least common multiple of 2 with itself. Well, least common multiple of 2 with itself is just going to equal 2. So elements that look like this, permutations that look like this, are going to have order 2 as well. And then we're going to have order 3 for my 3 cycle, and we're going to have order 4 for my 4 cycle. And so my group S4 has elements of order 1, 2, 3, and 4. Only 1, 2, 3, and 4. That's the power of this analysis that we just did, that we can only really do for sure for the symmetric group once we know what all the cycle types are. 1, 2, 3, and 4 are the only natural numbers that arise as the orders of elements in the group S4. Now let's think about the dihedral group of the dodecagon, D12. What kinds of elements are in D12? Well, let's write them. Not all 24 of them, but write enough of them as to give us an idea of what the orders of the elements all are. So remember, every dihedral group, after the identity, is going to have sort of 2 symmetries that can be taken as kind of the building blocks of all of the symmetries of my dodecagon. There'll be R, which is a rotation for the dodecagon, it would be a rotation by 30 degrees. It's 360 divided by 12. And then there's t, which is a reflection. It's just a reflection about some arbitrarily fixed axis of symmetry. And then this rotation is going to generate a cyclic subgroup consisting of a bunch of powers of r. And because my rotation is by 30 degrees, I come back around to the identity only after 12 iterations. So up to the 11th power of r, we get distinct rotations. Then if I take each of those and I prepend a t in front of them, I'm going to get a tr squared, a tr cubed, and so on, up to tr to the 10th, tr to the 11th. These are all going to be distinct elements from one another. And there is a complete list of what all the elements of D12 end up looking like. Now, one of the things we're going to talk about in Chapter 7, so that's the chapter we're going to skip over briefly, but I just want to make this point really quickly. This red highlighted subset of elements of D12 actually is a subgroup. Let's call it H. It's the cyclic subgroup generated by R. Right? Well, what about the other 12 elements in this group? Each of them is related to the elements in my first subgroup. Right? They look awfully similar, don't they? Each one of them is just the result of multiplying by t on the left. And so because of that consistency, we would call this set here, we would call it TH. My iPad is running out of memory on me here. Let me quickly disconnect and reconnect. Sorry, just having a little hiccup here. I just have too many slides in my presentation here. I'll come back up in a moment. So again, my point is that we can understand what all the elements in D12 look like. All of them are either a power of R, so an element in the cyclic subgroup generated by R, or they are equal to T times some element of R. So T times H is how I could write this set of elements here. It's not a subgroup, because in particular it doesn't contain the identity element, right? And so it can't be a group. It doesn't have the identity property. But it's called a left coset. Left coset of H. It's the result of taking the subgroup H and multiplying all of its elements by T, by one single element on the left-hand side. So it becomes what we call a left coset. And the important part about cosets is that the cosets of a subgroup partition the entire parent group, right? So I start with a subgroup that has half of my elements. This non-trivial coset exactly has the other half. Right? Okay, so that's what D12 looks like. But why we care is we want to do the same thing for D12 that we did for S4 a little while ago. We want to say, what are the orders of all these elements? What orders of elements exist in D12? And remember, we're looking for differences between D12 and S4. So let's start looking at some orders of elements. Maybe starting with the identity. Well, the identity is the low-hanging fruit. It's got order 1, always, every group. T, the reflection, is going to have order 2. What about the rotation? The 30-degree rotation of a dodecagon. What is its order in D12? Well, as I mentioned a while ago, we have to do that rotation 12 times before it comes back around to the identity. And so there's an element of order 12. It generates a cyclic subgroup of order 12 inside of D12. And immediately, we should stop, right? Because we have found an example of a number 12 which arises as the order of an element in D12, but not as the order of an element in S4. And so our proof here that D12 is not isomorphic to S4 can just be merely that D12 has an element of order 12, namely R, but S4 does not. QED. Right? If these groups were isomorphic, then that isomorphism would have to send R to some element of S4 that had the same order as R did. But there is no element of S4 that has the same order that R has. Right? D12 has an element of order 12, S4 does not, so they cannot be isomorphic groups. just for fun and just to reacquaint ourselves with the dihedral group, let's also list the orders of the rest of these elements while we're at it. Notice that all of the elements in this coset of the cyclic subgroup generated by R, everything that has a T in its representation, actually ends up being a reflection geometrically. When I compose a reflection with a rotation, the result is always a reflection. And every reflection is its own inverse. So all of these TR to the power elements, all of them are reflections, all of them have order 2. Okay. Meanwhile, in the cyclic subgroup generated by R, the order of an element is just going to be given by, well, this is exactly the what time is it clock activity that we did in class a long time ago. R squared is going to have order 6. R cubed is going to have order 4. R to the 10th is the inverse of R to the 2, so it's going to have order 6. R to the 11th is the inverse of R to the 1, it's going to have order 12, and so on and so on. Right? So in a cyclic subgroup, the order of each element is just the same as the order of the corresponding element in the group Z mod, in this case 12, because my cyclic subgroup had order 12. So this is why these two groups cannot be isomorphic. One group, D12, has an element with order 12, while the other group, S4, does not. So we had to know actually quite a bit in order to pull this problem off. We had to know how isomorphisms relate groups. In particular, we needed to know this order-to-order theorem that we proved in today's live stream. But we also had to have some really specific knowledge about the algebraic structure of both S4 and D12. So we had to understand how symmetries of polygons work on the one hand, and we had to understand how permutations of a finite set work on the other hand. So there was a lot that went into this. If I ask a question like this, depending on what I'm asking about the symmetric group, I could actually tag this to be a part of an assessment of your understanding of permutations in the symmetric group as well. So this is a great kind of question if I'm trying to get you on chapter 5 stuff as well as some other chapter, like chapter 6. All right, I want to go forward and talk about one last why are they not isomorphic kinds of questions. And this came from a particular question that, that one of you contributed prior to the live stream, so I want to make sure I get to this one before we wrap up. Why are the integers, the additive group of integers, Z+, and the rational numbers, Q+, why are those groups not isomorphic? Now keep in mind that when we were talking about isomorphisms of finite groups, when we were talking about D12 and S4 a minute ago, the first thing that we did is just find out what are the order of these groups, how many elements do they have, and in the case of D12 and S4, they had the same number of elements. Well, that same kind of thing is true for the integers and for the rational numbers. Both groups are infinite groups. And indeed, there is a bijection of sets from Z to Q. That bijection of sets is probably something that you saw in your introductory class to proofs and to formal axiomatic logic, because it's somehow surprising, it should be surprising, that we can put the integers in one-to-one correspondence with the rational numbers, that there are exactly as many of one of them as there are the other, despite the fact that the integers are a proper subset of the rational numbers. This is what's called, is often proven by something that's called Cantor's diagonal argument. It's what shows that, furthermore, that the Cartesian product of two countably infinite sets is also a countably infinite set. So there is actually a bijection. There is a one-to-one and onto function, probably many of them, between Z and Q as sets. So it's not the fact that they are different as sets that's going to give us a disagreement between Z and Q. It's got to be something about the algebraic structure, something about the operation that's going to make the two of these things different. So let's think about what algebraic properties that we can talk about. Let's take an example of an element in one of these groups and just ask a question about order. Order seems to be the topic of the day today. So let's say in the group Z+, what is the order of, I don't know, let's pick an element like 7. Well, this is an answer to the question, how many times do I have to add 7 to itself before the result comes back around to the identity element of this group? But the identity element of this group is the number 0. Well, we're talking about ordinary integers, the kind that you learn in 2nd and 3rd grade, right? And so this is just going to be 7 times n as integers. N is greater than or equal to 1 here, right? But 7 times n is always going to be greater than or equal to 7, and therefore can never be equal to 0. And so the order of 7 is infinite. And indeed, one of the things that we find out, this is not too surprising as long as you're thinking about the operation in these groups in the right way. And the claim is that every non-zero element of Q and Z has infinite order. And of course, 0 has order 1, right? Because it's the identity element for both groups. Again, this doesn't take too much persuasion to convince you why picking any non-zero element, if I add it to itself repeatedly, it's never going to wrap back around to 0 when the operation is the ordinary addition that we know and love of both integers and rational numbers. All right, so what this does is it tells me that I'm not going to find a difference in the orders of these two groups, and the orders of elements of these two groups either, right? They have a one-to-one correspondence of their elements, and they have one-to-one correspondences in the orders of those elements, because the orders are all infinite. So, you ask, isn't that enough to prove that these two groups are isomorphic? And evidently the answer must be no, because this problem is asking us to prove these two groups are not isomorphic. So what's the disagreement? Let's go back to our Highlander Theorem. Highlander Theorem is the theorem for finite cyclic groups. It says every finite cyclic group is isomorphic to Z mod n. There is an infinite version of this theorem as well. That, since we didn't get an opportunity to prove it here today, but the proof is completely analogous to the one that we did earlier on. So maybe I'll actually put it back up here. So remember, when we proved this theorem, the isomorphism that we constructed between a cyclic group of order n and the additive group mod n is just to take the exponent on my generator and relate that to the integer mod n. Right? 5x is equal to generator to the power x. So my exponents of my generator are what correlate to my integers mod n. Well, if we just remove the words mod n from that statement, we get an infinite version of the Highlander theorem that says that every infinite cyclic group is isomorphic not to Zn, but to Z, the additive group of integers. So let's add that bit onto the page here, just so that I can get it down as a theorem that we can cite for later on. So we'll call this the number line theorem. Back when I was talking about cyclic groups in Chapter 4, our introduction was that we should think of every cyclic group as either a clock if it's finite, or as a number line if it's infinite. And this is a theorem that makes the number line part of that concrete. So this number line theorem tells me the following. Let G be an infinite cyclic group. Then there is an isomorphism phi from G to the additive group of integers, Z plus. So there is my number line theorem. It's the Highlander theorem in the infinite order case. And I'm not going to go through all the details of the proof because they're completely parallel to the ones in the finite case, in the clock theorem. This proof is analogous to the proof above, with phi of x equals a to the x for a generator a of g. So I won't rehash the proof, but the very same way of constructing this isomorphism from Z to G is how we end up proving this number line theorem. So, coming down to here, we can say the following. If it's true, so let's make an argument by way of contradiction here, which we don't get enough opportunity to do, but it's kind of one of my favorite types of argument. Assume, by way of contradiction, that Q were isomorphic to z. Well, let's assume that Q were isomorphic to z. We'll come up with some way of deriving a contradiction. Well, by the number line theorem, this ensures that Q is an infinite cyclic group. So there exists a generator. And let me call that generator P over Q. After all, the elements here are fractions, they're rational numbers. So I'm going to say that there's a generator, right? And I'm going to call that generator the fraction P over Q as a rational number, right? So how are we going to show that this is absurd? We need to arrive ourselves at a contradiction. Let's go back to our scratch pad for a moment. So if P over Q generated the rationals, let's just work a quick example to see why weird stuff might happen. Let's say that my generator was 2/3. What is a cyclic subgroup generated by 2/3 going to look like? It's going to contain 2/3 added to itself any integer number of times. So it's going to be every integer multiple of 2/3. So that's going to be things like -6/3, -4/3, -2/3, 0, 2/3, 4/3, 6/3. Not reducing those fractions, I don't really care. Right? But that's what the cyclic subgroup generated by 2/3 is going to end up looking like. Right? And so you might say, well, if 2/3 really were a generator, that would mean that every single rational number would have to be in this set that I just listed. Can we find an example of a rational number that's not? I think that should be pretty straightforward to do. For example, this set skips straight from 0 to 2/3 without hitting any of the rational numbers that are in between. When you take real analysis, one of the first really powerful things that you learn about the rational numbers, before you even get to what the real numbers are, you learn that the rational numbers have what's called a density property. In between any two rational numbers, I can find another rational number that's not equal to either one of the originals. All I have to do is take the arithmetic mean of those two rational numbers, just the average. So in between 0 and 2/3, there's another rational number, namely 1/3. And 1/3 does not belong to this set. 1/3 is not an element of the cyclic subgroup generated by 2/3, and yet it is a rational number. And that's what's going to give me my contradiction. It shows why 2/3 is not a generator. Right? So just to bring that up to this example, if P over Q were non-zero, and if it generated the rationals, that would mean that half of P over Q would have to be, since it's an element of the rationals, it would have to be an element of the cyclic subgroup generated by P over Q. And so P over 2Q would have to equal K times P over Q for some integer K. But there is no integer K that can make this equation true. Depending on how you want to argue this, we could solve this equation and just argue that K must equal 1/2, which is not an integer. Or we could make some well-ordering argument or something to argue why my cyclic subgroup skips over half of my generator. But that's the core of the argument, right? That we're not going to be able to get everything because we're not going to be able to get 1/2 of my generator as part of my cyclic subgroup. So let's just write out that contradictory argument, and then we can wrap this up for today. Since A generates Q, we have that the cyclic subgroup generated by A is equal to Q. This implies that the rational number A over 2 must be equal to a power of this generator, right? Because it's a rational number, it must belong to the cyclic subgroup generated by A, because the rationals and the cyclic subgroup generated by A are assumed to be the same thing. But then, and this is our contradiction, right? A over 2 must be equal to K times A for some integer k by definition of cyclic. Right? A over 2 must be equal to some integer multiple of a. But the only k which satisfies this is k equals 1/2. The only rational number k that satisfies this is k equals 1/2. But 1/2 is not an integer. And that's my contradiction. And so just to wrap up the argument here, oops, erase some stuff I didn't want to erase. There we go. So just to wrap up my argument, thus the assumption that Q is isomorphic to Z is absurd. Put my little tombstone at the end of the proof, and then we will call this done. Sorry, I'm getting my stuff back onto the screen here, and space this back out the way I wanted it. Cool. And just scroll down a little bit so you can see the whole proof. Right? So if we were to assume that Q is isomorphic to Z, then Q would have to be a cyclic group. But any generator that I can try to pick for the rational numbers is going to miss something. In particular, it's going to miss the rational number, which is equal to half itself. It's going to miss a lot of others too, but we can show that it definitely misses half of itself. And so Q is not a cyclic group. Basically, that's the shape of this proof. Q is not isomorphic to Z because Z is cyclic. Q is not. Z has generators. It has 2 of them. 1 is a generator, and so is its inverse, -1. 1 and -1 are each generators for the integers. But Q is not a cyclic group. And so there's no isomorphism that could relate the generators of Z to generators for Q. So that's going to wrap up today's live stream. Isomorphisms are one of those topics where we could seriously go for hours. There's lots of stuff to explore here. But I hope this has given us a good sort of flyover of the various topics that we can talk about in this chapter. So we proved that there can be only one, that any finite cyclic group is isomorphic to Z mod n. And therefore, any group of prime order, which is guaranteed to be cyclic, is isomorphic to Z mod p. So Z mod p is the only group of order p up to isomorphism. We also showed that isomorphisms preserve the order of elements, and we can use that fact to find a lot of differences between 2 groups that superficially might seem like they should be the same, but if we find a difference in the orders of elements, those groups cannot be isomorphic for that reason. We also showed that S4 was not isomorphic to D12, because D12, the dihedral group, had an element of order 12, but S4, the symmetric group, did not. Its only element orders are 1, 2, 3, and 4. And then finally, we showed that the integers and the rational numbers were not isomorphic, because while the integers form a cyclic group, the rational numbers do not. And the reason the rational numbers do not is because they have this cool density property that you'll talk about more when you take a course in the Introduction to Real Analysis. But the very fact that the rationals have this density property means that they cannot be generated by a single one of their elements, whereas the integers can. So we're going to wrap up today's live stream there. We'll take the quiz on isomorphisms tomorrow, and then we're going to skip Chapter 7 for now and move forward to Chapter 8, where we talk about the direct products of groups. How do we take 2 groups and glue them together to form a new, larger group? Ultimately, our question about how many different kinds of groups can exist of a specified order is going to require us to learn how to break groups apart and how to reassemble groups back together. And the direct product is going to give us our tool for taking 2 groups and assembling them into a larger group. It's our main building tool that we're going to use to make bigger groups out of simpler groups. And we're going to dive into that as our next topic after we get done with isomorphisms. I look forward to doing that with you next.